Hello everybody, this is the fifth clip of our chapter 3. This video clip will be about the equation of the line. So the equation of the line will got three forms that we usually use, and also the equation of the planes. Okay, so let us begin with the equation of the line. Alright, so here the line L in three-dimensional space is usually determined by the point R0 right here, the point that this line is passing through, and the vector V, okay, which is the direction that is parallel to this straight line L. Okay, so to determine the first form of equation of the line, which is the vector equation, it is based on the knowledge of the parallel of two vectors. So your u is parallel to the v if we got u equals to kv for some real number k. Okay, so this is the definition of the parallel of two vectors. So here the line will also like somewhat a vector, right? You can regard it as a vector that is parallel to the v right here. Okay, so to create the vector along this straight line, we just pick up one of the arbitrary point on this line, we call it the r, and then we are going to connect these to terminate point. Okay, when we talk about a terminate, then it means that we create the vector that is pointing from the origin to the r, and then also the vector from the origin pointing to the r0. Okay, so the one that is begin from r0 and then terminate at r, this one is actually the vector r minus r0. So from the picture we can see immediately that r minus r0 is actually parallel to v. So it means that there is a constant t. Okay, we are going to use t instead of k, such that your r minus r0 equals to tv. Okay, so this means that in terms of equation, okay, your r is arbitrary point on the straight line will be equals to the r0 plus tv. Okay, even though I just saying that this r is an arbitrary point on the straight line, but as you determine the point on the straight line, you can immediately construct the vector from the origin to that point. Okay, so in terms of equation, it's actually the on the left hand side is a vector, and on the right hand side is also the vector. Okay, so the equation of the line, which is so-called the vector form, it takes r equals to r0 plus tv. So the r0 is the point that your line is passing through, and the v is the vector that your line is parallel. Okay, so as we have this equation, we can extract this one a little bit. Okay, so your r, because your r is actually, as I told you, arbitrary point on the line, so actually your vector r can be regarded as x, y, and z for each of the component. Okay, and we let your r0 to be x0, y0, z0. So this is the point that your line is passing through. Okay, and we say that your v is actually a component of a, b, c. So for the vector equation, we know that your r is actually your r0 and tv v, simply like this. Okay, so the vector on the left is equals to the vector on the right. So what does this mean? It means that each component, they are the same. So your x is actually x0 plus ta, your y is actually y0 plus tb, and your z is z0 plus tc. Okay, so this one is actually the point that is passing through, okay, that your line is passing through, and this ABC is actually the component of the vector that your line is parallel. Okay, so we got this form of equation of the line. So this one is also called the equation of the line, but it is the parametric form. Okay, parametric form. And parametric is mean that this form got a parameter, and actually this t is your parameter, right? So here is the form, okay, the one that we told you, a parametric form. Okay, so it's x equals to the point and the vector is parallel, y equals to the point and the vector is parallel, and z equals to the point and the vector is parallel. Okay, so for example, if you need to find the vector equation and the parametric equation for the line that is passing through this one, so here's your r0 and there is your v. So if you're talking about the vector equation, okay, it is very simple. So you got r equals to your r0. So now just don't forget that at the beginning this is the point, but when you talking about the equation of the line, on your left hand side is a vector, so on your right hand side everything must be the vector as well. So you change your r0 as a point into the r0 that is the vector pointing from the origin to that particular 3, 2, 0. Okay, and then don't forget that the vector equation, you need to plus the t and then multiply by your vector v that's parallel, which is 3, negative 2, 1. So that's very simple. But if we need the parametric equation, there's another simple as well. So you got x, okay, which is the first component, equals to the point, okay, the first component that your point is passing through, and then your first component of the vector is parallel. For the second component, we got the second component of the point, we got the second component of the vector parallel multiplied by t, and then for the third component, you got the third component for the point that's passing through, and the third component of the vector that your line is parallel. Okay, that will be it. Okay, and you need to bear in mind that sometimes your one of the ABC, okay, may be 0. So for example, if your v is happen to be 2, 3, 0, okay, then let's say that your r0, the point that passing through, is 1, 1, 2, then the equation of the line using the parametric form will be x equals to 2 plus 1 t, y equals, is the point first, so it's 1 plus 2 t, 1 plus 3 t, but your z is just simply 2 and 0 t, so we just write z equals to 2. Okay, and that's it. We're right. So let us look at the parametric equation again. Okay, so let me just write down one more time. X equals to x0 plus at, y equals to y0 plus bt, and z equals to z0 plus ct. And then from these equations, let us solve for the same parameter t, because you see there are common parameter t. So if you solve for t from the first equation, you got x minus x0 over a, and the second equation you got y minus y0 over b, and then the t also equals to z minus z0 over c. Of course, I mean all these equation you need your a b c is not 0 because you have it as a bottom, right? But each of them equals to the same t, so it means that your x minus x0 over a, your y minus y0 over b, and your z minus z0 over c, they are all equal. So this one is another representation of the equation of the line, and this kind of equation of the line is called a symmetric form. Okay, a symmetric form. So this symmetric form contain no t, but the one that is together with your x, your y, and your z on the top is the point that is passing through, and the one at the bottom is the vector that your line is parallel. Okay, but the way we obtain the symmetric equation is actually to solve for t on each of the parametric equation. So of course, if one of them, and this is a special case, if one of them, let's say a equals to 0, then we are going to separate it. For example, this one, because you got no t for this equation, right? And then usually we separate it by a semicolon, and then the rest can be equal just like that. Okay, so if one of them is 0, you need to separate the 0 out from the others. We get? So this is what we just said about the parametric equation. So let us try this example. You need to find the the symmetric equation. This one is a symmetric form. So let us find the parametric and also a symmetric equation of the line that passing through these 2 points. Okay, so now I mean these 2 points, actually we still don't have a vector that's parallel. However, from the 2 points on the plane, we can just simply find the vector that is passing through these 2 points, right? So let me do it like typical way. So usually we do it from A to B as a vector, right? So let's say, what is your vector AB? So it is a B minus the A. So your B is a 5 and then 1, a 0 and 2, and then 2 and negative 1. And you got a 4, a negative 2, and a 3. So this one is the vector that's parallel to our line. Okay, and then you can choose either your A or your B to be the point that is passing through. So because your B contain a 0, so let me just use this B as your point that is passing through as 0. So first, a parametric equation will be x equals to the first point, and then the parallel vector, y equals to the second component, and the parallel vector second component, and z equals to the third component, and the third component parallel vector. Okay, so this is your x, y, and z. How about your symmetric equation? So it will be x minus the first component that is passing through over the first component of the parallel vector, y minus the second component that is passing through over the second component of the parallel vector, and z minus the third component over the third component of a parallel vector. So this is the symmetric equation of this line. And they also ask at what point or at which point does this line intersect the xy, the xz and the yz plane. So let us talk about the intersection of the xy plane. Okay, so if you want to know the intersection of the xy plane, then it means that your z must be 0. So let's look at the, you can look at either one of them, but let me just first look at this parametric equation first. So your z is the last equation, right? And then now you need your z to be 0 in order to get the intersection. So it means that your 2 plus 3t equals to 0. So it means that your t is actually negative 2 over 3. Okay, so as you got this parameter, then you know that your x will be 5 plus 4 negative 2 over 3, okay, which is 15 minus 8 over 3, and it is 7 over 3. And then your y is negative 2 multiplied by negative 2 over 3, which is 4 over 3. So it means that the intersection point, it is simply your x, your y, and your z must be 0. Okay, so this is the intersection point of this straight line with the xy plane. Okay, on the same token, if you want to find the intersection point of the xz plane and the yz plane, okay, what is it that you do? So to find the intersection of your xz plane, you let your y become 0, and again solve for t and use this parameter t to determine the x and the y. Okay, so you use this parametric equation right here. Okay, it's not that difficult, right? How about the intersection of the yz plane? Then you are going to let your x equals to 0, and again solve for t in this parametric equation. Okay, and then after you got that t, you just plug in your t into the rest of the component to get the point of intersection that you need. Okay, so let us continue a little bit. The first one is the so-called the line segment. Okay, so here if you have your R0 on the three-dimensional space and R1 in on the three-dimensional space as well, we need to determine the equation of the line segment. Okay, only the segment starting from R0 and terminate at R1. That line segment will be very easy. Okay, so it is consist of two parts. Okay, so this one is the line segment, the equation of the line segment. Let us call the RT. This one will consist of 1 minus t and then R0 plus t R1, and your t is between 0 to 1. So let us try to plug in. If your t is 0, then your R1 disappear and your t right here is disappear. So you end up with R0, which is the initial point. If your t is 1, then you got this one is 0, this is 1. So you got your terminate point R1. Okay, so this one is just something for you to look at it, and then it will be useful later on. Okay, another concept about the two line in three-dimensional space is that it's not really the same as in two-dimensional space. Okay, in 2D your two lines either parallel, okay, or intersect to each other. Okay, so if it's parallel, then it means that it's not going to intersect, and if it intersect, it means that it's not going to parallel. Okay, however, in the three-dimensional space, okay, I'm not so sure whether, because as we cannot see each other, okay, we're not so sure whether we can write this one or not. Okay, one of the relation can be the two lines, they are parallel to each other, just like this. Okay, or they can cutting each other just like that at one point. However, think of it this way, there will be another relation in three-dimensional space. Okay, think of it this way, if for example one of the line, they are on the floor just like this. Okay, they're on the floor, and one of the second line is on the ceiling of your room. Okay, on the ceiling is of your room. All right, and then of course they are not parallel to each other. Okay, they actually want to intersect each other, but they are on the different level or on a different plane. Okay, they actually on the one of the plane which is called, okay, let us call this plane on the floor, which is z equals to 0, and the second one may be contained in the plane that is elevated, I mean just the one that's parallel to z equals to 0. So it is let's say z equals to 10. Okay, so actually if they are on the same plane, they'll intersect each other. However, right now they are on a different plane, and these two planes, they are parallel. So it means that the red line here, the one up here, and the blue line on the floor will never meet, right? It's not going to intersect to each other, and they are not parallel. Okay, they are not parallel. So if the line is not parallel, is not intersect, we'll call these two lines are skew. Okay, these two lines are skew. So let us show that these two lines that's given here are skew lines. Okay, so first let us try to see whether it's parallel or not. Okay, so for the two lines that's parallel, then it means that, let's say this is L1, this is L2. For your L1, there will be the V1, the vector that your L1 is parallel, and there will be your V2, the vector that your L2 is parallel. So if your L1 is parallel to L2, it means that these two vectors are parallel. So it means that there will be a constant k such that V1 equals to k V2. Okay, and this k must be only one number, okay, for each and every component. So let's look at your L1. Your L1 got the V1, so it is the one in front of your T. Okay, the vector that's parallel, so it is -1 to -1. And your L2, the V2 is the same thing, only the coefficient that is in front of your T. So we got 1, -4, and 1. Can you see here the one in front of the T? So let us assume that your V1 equals to k V2. Okay, let us assume, so just pretend. So it means that the first one, it is -1 equals to k1, so your k can be -1. The second component, you get 2 equals to negative 4k, right? So it means that your k is simply 1. I'm sorry, this is on the first one, because your negative 1 equals to k1, so your k is negative 1. On the second one, your 2 equals to negative 4k, so it means that your k is negative 1/2. So you got a different k, okay, from the same relation. So it means that our assumption cannot be true. So it means that your v1 is not parallel to your v2, okay? So it's already not parallel. Okay. Now we want to determine whether they are intersect to each other or not. So if they are going to intersect to each other, it means that they're going to share the same point, is it? They're going to share the same point, okay? So to do that, actually, if we use the same parameter t in both of the equation of the line, that will be very difficult for you guys to see, okay? So usually if we got two lines, okay, on the same problem, one of them we will use one parameter, another one we are going to use another parameter, let's say s, okay? So the parameter on the first line and the parameter in the second line maybe have the different value, okay? However, to check the intersection, so it means that they must share the same x coordinate, the same y coordinates, and the same z coordinate. So the very easy way to look at is that your x must be equal, your y must be equal, your z must be equal. However, if your x equal, then you see that you got two parameters t and s. If your y equals, you also got two parameters t and s. So these two equations will be good enough to solve for both t and s. You know what I say? So you got 3 minus 1, 3 minus t must be equals to 1 plus s, okay? So this one you are going to share the same x, and to share the same y you have 1 plus 2t must be equals to 3 minus 4s, okay? This one, the equation that you share the same y. So for the first equation, let us rewrite it. So you got t plus s, so I move the t over there, and then move the one back here. So your t plus your s becomes a 2, and the second one you got a 2t and 4s, okay? So I move it here, equals to 2 as well, or you got a t plus 2s equals to 1. So by these two equations you can just do a subtraction, right? Upon subtraction you got s, you use this one first, okay, the bottom first. So you got the s equals to negative 1, okay? So if you got your s equals to negative 1, then your t, okay, you can just plug it in here, right? Your t is 3, okay? Then I mean this s and t, you are going to get the same x and y in both what, L1 and L2, okay? But what else that we need if you want your two lines to intersect? Not only the same x and y, but also the same z, okay? So we are going to check if your t is 3, your z on the first L1, so this is your L1, so let us go back a little bit. Your L1 is 1 minus t, so it is 1 minus t, which is 1 minus 3, so your z is negative 2, and your s is negative 1. So the second straight line, your s is simply your z is simply the s. So here for your second line, and your s is -1. So from these two first equation, you got the same x and y, but by these two parameters you got a different z. So what does this mean? It means that your intersection can never occur. So your L1 and L2 are not intersecting each other. Okay, so if your L1 and L2 first is not parallel, second they are not intersect. Okay, so let me just complete this one, because your V1 and V2 is not parallel, so it means your L1 and L2 are not parallel to each other. Okay, so this is what we can conclude. So it's not parallel and it also not intersect, so it means that your L1 and L2, they are skew lines. Okay, so it means that they live on a different plane. Okay, and those two planes are parallel, but your L1 and L2 are not parallel to each other. Okay, so this is the so-called skew line. All right, next let us talk about the plane. Okay, let us talk about the equation for the plane. The for the plane, okay, it is simply a straight sheet of paper, right? So we cannot say that we want to determine the plane by the vector that's parallel, because there will be several vectors, okay, that's parallel to this plane. Okay, that's too many. So if we cannot do that, we look at it on a different angle. Okay, so from this straight sheet of paper, we can actually determine it by the vector that is perpendicular to this plane. Okay, and it will be only one vector. This one is so-called a normal vector. And of course, I mean, this plane can elevate at any level. So to fix it to one level, you need to know the point that the plane is passing through. Let's call this one the point P0, which is x0, y0, and z0. Okay, so to determine the equation of the plane, you just pick up one arbitrary point on the plane called x, y, and z. Okay, and then you are going to find the vector here. Okay, this vector start from the point that passing through and terminate at the arbitrary point x, y, z. So this vector is simply the x minus x0, y minus y0, and the z minus z0. Okay, and this black vector, okay, because it is on the plane, and the red vector over here, they always perpendicular to each other, right? Because this one is parallel to the plane, this one is the one that perpendicular or orthogonal to the plane. So what does this mean? It means that if you dot these two vectors together, let's say n dotted with x minus x0, y minus y0, and z minus z0, it must be 0 because of the dot product of two orthogonal vectors. Okay, there must be 0. So let's say that your n, the one that is perpendicular to the plane, is the vector ABC. So you got a and x minus x0 plus b y minus y0 plus c z minus z0 equals to 0. Okay, and you can just calculate your a and x, your b and y, your c and z, and then the rest, okay, ax0, by0, and cz0, they're just numbers, right? So they can add it to each other to get the d and equals to 0. This one is so-called the linear equation in terms of x, y, z, of the linear equation of the plane, okay, in terms of x, y, z. All right, and the equation of the plane usually in this form, okay, usually will be in this form. So if you look at this form of the equation of the plane, it is easy to tell that the number in front of x, y, z is the component, okay, each component of the vector that's perpendicular to the plane. However, it is difficult to tell what will be the point that your plane is passing through, okay. So as we continue, I'll let you know how to find it, but the easy way to do it is that you just let your x to be 0, your y to be 0, and then you solve for z from this equation. That will be definitely one of the point that your plane is passing through, okay. So we are going to stop this clip at this point, okay. So for this video clip, what you have learned is about how to construct the equation of the line, okay, and the equation of the line contain three forms, okay, which is the vector form, the parametric form, and the symmetric form, okay. So the vector form, it is r equals to r0 plus vt, and the parametric form, it is x equals to x0 and at, y equals to y0, sorry, this one has no vector, y0 plus bt, and z equals to z0 plus ct. And the symmetric, it is x minus x0 over a, y minus y0 over b, and z equals to z minus z0 over c. And this one, your a, b, c, they are not 0, okay. So if one of them is 0, then that will be something else. And the line will determine by the point that it's passing through, and the vector that's parallel, okay. For the plane, that is a little bit easier, okay. You got the vector that is perpendicular to the plane, let's say ABC. This one is called a normal vector, and the point that your plane is passing through, and then the equation of the plane or the linear equation will be a x minus x0, b y minus y0, and c z minus z0 equals to 0. But usually the form that you see in the problem will look like this, okay, ax by cz plus d equals to 0, okay. We'll stop it right here, and then next time we'll continue from here and then try to solve several problems involving the lines and the plane. We'll see you then. Bye bye.